Let's continue reviewing alcohol's reactions, and I have that molecule, and we're gonna see what is the final product after you treat it with all these reagents that we have. So it is the same molecule that we have in other videos, but we're using different sets of reagents. So let's get started with this. And all right, so first reaction says tosyl chloride. So when we are doing reaction with alcohols, alcohol is a bad leaving group. So if you're going to do a substitution, you need to transform the OH into a better leaving group. When we do that under acidic conditions, we transform it into water. So we protonate here. But notice that after this reaction, we're treating with detoxers. So clearly we need a good leaving group, and we're working under basic conditions. So this reaction is used to transform that OH into a good leaving group, into tosylate. So let's draw that. So the first reaction here is, I'm going to do transforming the OH into a good leaving group, OTS. What I want you to see here, and that is important, is the stereochemistry. That reaction had happened at the oxygen, so it didn't touch the chiral center that we have here. Therefore, the configuration of the chiral center didn't change, so it happens with retention of configuration. So that's one important thing. Again, you didn't do an SN2, you didn't touch that carbon, that is your chiral center. And that means that you are not changing the configuration, so retention. Let's work now with the second reaction here. So now in your second reaction, you're treating that with etoxide. And so this is a strong base, strong nucleophile. We're going to be doing an E2 reaction. But what we need to remember here is that E2 reactions, for that to happen, you need to have a beta hydrogen that is anti to the leaving group. And here, just to go briefly over that, we see here that in that molecule, to this side, you have a hydrogen. You do. But it's not opposite. It's not anti to the leaving group. However, in this position, you have two hydrogen. One of them is opposite to the leaving group. You see one in dash and one in wedge. You could also picture this using the chair. So if you use a tosyl pointing up, you will have this hydrogen pointing up and this pointing down, and this is how you want it for the E2. And for that reason, because on the other side, you have the hydrogen is pointing up, so it's not anti-periplanar. What you have opposite is the ethyl group. So, and that is important because now typically this is a small base, so you will form the Sisa product. But to this side that will give you the Sisa product is not happening because the hydrogen is not in the appropriate position. It's not anti. So in this case, you will get the elimination with this hydrogen, which is not actually giving you a Sisa product. So this is your elimination. And what I did is essentially this, I already have highlighted here, this and that, which are opposite, are those the ones that are gonna go. And we're gonna draw now the final product will be after reaction number 2, right? Now we're making the alkene here, and we still have the ethyl in the same way we had it before. I'm just gonna go a little bit over. It's not showing much, so that's why I'm kind of making it bolder. Okay, so that's my alkene, and the explanation that you had the least substituted alkene is because you didn't have that anti-conformation to get that elimination. So next reaction is treating that with ozone and dimethyl sulfide. So that's my reaction number 3. And what that does is ozonolysis, which is you're breaking this double bond. I'm not going to go over the mechanism, but you form the ozonide, several intermediates, but the end product, you're going to insert an oxygen here and here, so on both ends. So this is, I'm going to draw it initially as, say, cyclic structure, and then we're going to extend it. See what it looks like. So now I'm copying that. This is my ethyl, and now on this, and I'm gonna insert that oxygen. And I'm also going to be doing that to the other end. So see that here? Looks a little crowded, so we're gonna have to extend it. But still, you have 1, 2, 3, 4, 5, and 6 carbons. So that's what I'm doing. On one end, in this, notice, is an aldehyde. That's another aldehyde. So carbon 1 and carbon 2, we're going to have this ethyl, carbon 3, 4, 5, and 6. So 1, 2, 3, 4, 5, 6, that's another aldehyde. So these are the same molecule, but now one is drawn extended. And that's the final product for these reactions. So pay attention to the stereochemistry and to the mechanism, because if you didn't do that, you may get the wrong product. We need to make sure that we know the mechanism and to see that this needs the the beta hydrogen being anti to the leaving group, and that will help you predict the products.